going to look at another problem. So this is example number 3. So again, they ask us to find the stresses at point H. Okay. So again, identify what are the torque, what are the moments, what are the shear force. So again, the first thing we do, given to us, this is our transformation. X is our Y, and this is our Z. And element H is over there, and then we have to identify where our centroid is. So this is our centroid. Okay, so there's our centroid. The force of 13 kilonewton is applied at an angle. So now, if it's an angle, we have to break it down into its components. Okay, so we know that we will have a dy over here. Okay, so sorry, wrong color. So we know that we will have a dy, and we know that we are going to have a dz. And we have to, you can use an angle, okay? So we're going to call this theta. So we find what is our theta first. So tangent theta is equal to 125 over 300. So theta, so it's equal to 125 by 300. Inverse tangent 22.6 degrees. So from here, we know that dz is equal to 13 times 10 to the power 3 multiplied by sine 22.6 degrees, right? Or I better write this properly, sine of 22.6. Okay, so sine 22.6 times by 13 power 3 is equal to 4996 Newton. And then dy is equal to 13 times 10 to the power 3 cos now 22.6. Okay, so cos times by 13 to the power 3 is equal to 12,000. Okay, 1202 Newton. Okay, so now once we have this, right, again, same procedure. We're going to put this in our, we're going to look at this on our XY plane. Okay, so we are going to view this in our XY plane. So this is X and this is Y. And then we have 300 So I will sketch this out. Okay, so okay, and then we have something like this, then 150, and then it's gonna come here. Okay, and it's built in over here. And then we have our element H. And then we draw our centroid relative to the element of interest. Right. Then we have a load coming down, which is equal to 12,002 Newton. And we have a load going away from us, right, which is 4996 Newton, right? So from here, we ignore the dots and crosses, right? So we know that this is also our rotation in Z. Okay. So immediately we know that we have a case of eccentric bending over here, right? So the 12,002 is parallel to the what? To the centroid. And then we know that there will be an axial load applied down here, right? There's an axial load applied down here. So this will be also equal to 12002 Newton, right? So we know that Py, why Py is acting in the y direction. Okay, so we know Py is equal to minus. Why is I say minus is acting into the what? The element is going to induce a compressive stress. Okay, so element H will be negative. So for this case, we know that stress in the y direction is equal to Py divided by area. Okay. So the next thing that we are going to look at, we know that there's a moment. So I'm going to call positive this way, right? Moment in the Z direction. So this 1200 is parallel to the what? To the centroid. So we are going to take the perpendicular distance like this. So that distance over there is equal to what? Is equal to 0.15 to the centroid, not to the element, yeah, to the centroid, right? You have to be really, really like careful over here. So this we're going to have 12002 multiplied by 0.15. So this is equal to 12002 is equal to 1800.3 Newton meter. And it's going to have a moment in the Z direction this way. So we know compression, and this side is tensile. So we know that element H is going to be negative based on the formula. I'll just write up the formula. Stress Y is equal to mz over izz multiplied by x. Okay. So we know that it's going to be compression. Okay. Anything more? No, there's nothing for us to analyze. Then we look at another point of view now. Okay, so we change another point of view. Okay, so let me copy and paste it so I can draw I don't need the image to be so big. So the next thing that we're going to analyze is we're going to analyze on the YZ plane. Okay, we're going to analyze on the YZ plane. So now we're going to draw YZ plane. So this is Y, this is Z. So I'm just going to sketch this out. Okay. And this is where our element H is. And then we know that we are going to draw our centroid. So we know that there's a load coming down. This is the 12002, right? And then there's a force going this way. And it's going to be what? It's going to be 4996. Okay. So from here, we know that we are going to have a VZ. Right? We know that we're going to have a VZ, a shear stress. And the VZ is equal to 4996 Newton. And element H is a centroid, so we say that element H, okay, is not equal to 0 when we apply the formula. The shear stress is equal to VZ over Ixx Ux over T. Okay. So it's not going to be equal to 0, right? If it's on the surface, then it will be equal to, I mean, if it's on the furthest distance away from the centroid, then it will be equal to 0. For this case, it will not, as you can see. And then the next thing that we are going to do, right, the 4996 now is acting perpendicular to the centroid. So we do have a perpendicular distance from here to here, right? And that perpendicular distance is 300 minus by 200, so it's 0.2 meters. Okay. And then it's going to induce a moment. So I'm going to, I do apologize. This is rotation about X. Okay. So we know that we are going to call positive rotating in this direction, right? So we have moment X. So we are taking moment at the element, right? Is equal to 4996 multiplied by 0.2. So 4996 is equal to 999.2. And what we know is exactly at the centroid. So element H is equal to 0 and Y is equal to 0. If we apply moment about X over IZZ, right, multiplied by the IXX, multiplied by the Z distance, right, the whole thing will be equal to what? And the Z distance at element H is equal to what? 0. Okay. All right. So anything else? No, we don't. I don't see anything else that we should be